Hey folks, I set it for Saturday. I don't know what I was thinking. I guess I wasn't. But I'm gonna close this door behind me because it really irks me that I don't see my logo. See if I can't fix that. Oh, somebody's in there already. Hello. I've got some things I want to do. Specifically, hey, there he is. Hey, Hollywood. Let's see. Middle screen splaining. I'm waiting. Right. It's my height above ground. Real 30 feet up. And actually, this is the long wire. Yeah, this is the long wire. We need to do something new. I need to save this, though. Links in the description there, Hollywood. He said you got this. Let's see. This is Ziggy's. I think I already saved it. We'll call it 300 foot, maybe. Let's go new. Ape asked me a really good question. What does it take to find out the impedance of a wire? Right, so what do we... Is that a 40 meter wire? Yeah, it's a 40 meter, and then we're gonna have to use a calculator. I would like to know the exact. So I hate to ask, but I'm gonna have to ask. Grockadoo. 0.05% length of a 40 meter wire. Let's just say, I know what I've done. Sorry, 5% of a 40 meter wire. There we go. 2 meters exactly. Okay, I can do this. I'm gonna just draw something, and then we'll edit it. Wire def. Change. Oh, look, I was close. 2 meters or 4 meters. I'm gonna change that to 2. Here's my 2 meter. That's strange. 6 feet. I always thought it was more than that. 2 meters. How many meters? 5% of a 40 meter wire is 2 meters, which is 6 feet. But why do we always use 17? We'll run it and we'll see what it does. Okay. I need to wire 1 base. See where that landed me. Nope, I mean, not base, beginning. We'll do wire 1 end, because I drew it from that way. Yeah. And let's run a fundamental on it. Should be good to go. Yep, that's what I'd expect. Let's get a jelly bean up in this business. Frank played that Rickroll song, and now it's stuck in my head. Never gonna give you up. That's funny. Let's take the pattern away. Let's make sure everything's doing like I want it to. Yeah, okay, this is all good. I want to now see what's going on here at me counterpoise. So this is interesting right here. This is a neat tool I wish I had known about. All corners. I don't know how to use this tool. It's like a shifting tool. Hit that like. Thanks, Liberty Cave. You can jump in for audio if you want, Liberty Cave. I don't think I've ever had the pleasure of talking with you. Rotate. Rotate? Move. It's still that move. I don't know how I did it. Hollywood had me figure it out last time. And I've lost my current. Well, I think something's changed here. Okay. So let's look at some math, right? I am just on a cheap tablet, Ziggy. Well, then jump in for audio, man. You don't have to share a camera. Thanks, Eamon. I appreciate that, dude. It's nice of you. All right, so we have a whole bunch of ohmage issues, and I think that might be because we're 10 feet above ground. It's because we have this, right? Our feed point impedance. So it's talking about 6,000 ohms. So what is it going to? Oh, hey, Hollywood.
Howdy.
Hey. So 6,000 ohms, right? What happened to the expected? What is it? 49 times 50 gives us. What do they say? Like 20, like 2,000, 3,000 ohms. Let's see. Calc. What'd you do today, Hollywood?
What did I do? That's the
Oh, there it is.
$64,000 question. I don't know.
Probably the 18th
I
time.
stayed out of trouble, and it wasn't any fun.
2450. Okay, that's right. So
you can slide me off of the screen because I'm taking up half of the real estate.
I didn't notice that. There we go.
There you go.
2450. So that is your typical 49-to-1. What we assume is going to be the impedance transformation. Ape asked me a really good question, and I kind of have a hard time phrasing, more or less putting it into a better context. Let me see if I can't read it verbatim, the question in particular. And then I just blabbered at the mouth for him for a while. Tell me about the resonant point you see in a 49-to-1 in-fed half-wave transformer. Oh, I love questions like this. Oh man, this really gets me fired up. So 49-to-1, so that would be our 50 ohms times 49 lands us at 2450. Now I've modeled a fundamental 80 meter in-fed half-wave, and I guess the standard, thanks Liberty Cave. I guess the standard impedance ratio everybody seems to gravitate towards is 49-to-1, and I think a lot of people, I understand they've got like an antenna, like a 64-to-1, 56-to-1, 49-to-1. It's amazing that there's so many hams that think that these are different antennas, right?
Mm-hmm.
It's kind of like Nike and Reebok and Adidas. Like I'm like, no. This is all the same. We always start at the end here. Frank's Frank got to sit down and eat some supper finally. Good on you, Frank. The calculated impedance here now. Which one do I look at, Hollywood? Do I look at JX or do I look at overall resistance?
Okay, so they're actually it's a combination. So think of do you remember Pythagoras? A squared plus B squared equals C squared.
Yes.
Does that ring a bell? Okay. So in order to get the total impedance, it's R squared plus jx squared. And then you take the square root of that. And I probably just pissed off a whole bunch of people because it's math, but you can do it this way in your mind's eye. We'll keep it real simple.
Okay.
If you draw a triangle, so you've got a horizontal line, and it comes to, yeah, go ahead, because this picture is worth 1,000 words.
One triangle coming up.
Well, just draw.
Oh, hey,
Okay,
that's not a triangle. What happened to my
yeah,
triangle tool?
draw a horizontal line first.
A horizontal line first.
Yeah,
Horizontal. That's
lose the triangle and
Control Z.
yeah.
One line. Roger.
Okay. On the right-hand side of the line, draw from that point, go up a little bit. So draw a vertical line from there up. Yeah, about to there. Yeah, perfect. Okay. And now from the two open ends, close them up with another straight line. So it's down at a 30-degree angle down to the left.
I wonder if I could have done that.
Sure.
Yeah. So let me. But we're gonna do it from this way.
It doesn't matter.
Does it only go? Does it
It
only draw
doesn't
one
it
way?
doesn't matter.
Okay. Oh, that's so strange. Why?
If you spin it to the right, it would make more sense because it'll line up with the Smith chart.
Okay. Well,
But
I'll just
once you see this, it'll make a lot of sense.
Oh, I'm excited.
Yeah.
Okay. Here we are.
So the horizontal line at the bottom is your R.
This is our R.
Mm-hmm.
Oh, I need to go freehand. Oh my word.
I'm glad I'm not the only one who has difficulty.
The geniuses come out once MS Paint is launched.
Right. The vertical wire is your J or your X. They're one and the same. Yeah.
Our J/X.
Yeah. That's the complex impedance. So R is the resistance, and the J and the X is what we looked at on the other on Manigal, right? There's those two numbers. The hypotenuse, the last remaining, is the Z. It's a combination of those two. Right. Z for Ziggy. And it will always be longer. It's the square root of the two combined, basically. Yeah, right. Etch a sketch, right? So now if you can, in your mind's eye, picture the background paper, instead of being white, is a Smith chart. I wish we had an overlay, but try to do it in your mind's eye. And the point on the left
Is this the
is
bullseye?
yeah,
Okay.
that's the bullseye,
I
right?
gotcha. Maybe. Not necessarily. How to
Yeah, you might be
circle.
able to do that.
How to
Yeah,
circle.
yeah. And then you'd have to make the triangle a lot smaller, but then you're gonna lose the letters
Yeah.
if you do that. So this is fine. So the center of the bullseye is where we want to be. That's our 50 ohms. So as I go to the right of the bullseye, my resistance goes up. And conversely, if I went to the left, the resistance goes down. So that's our equator on the Smith chart.
All right.
And
Oh,
go ahead. You got it.
Yeah. Oh, yeah. Close enough. All right. So this is positive, positive resistance.
Right.
This is negative resistance.
Right.
Okay.
Okay.
But that's all.
So the J or X is our reactance. So if it's above the equator, it's inductive. And if it's below the equator, it's capacitive.
J is going to run this way with a straight line. And we're going to have a freehand. We're going to be inductive and capacitive.
Good.
Yeah.
Perfect.
All right. Wish I'd get rid of whatever this is. Anyway. And
So
yes.
so if I have some resistance that's higher than the bullseye at 50, it's going to be somewhere along that horizontal line. And from there, I either go up or down. What we're doing is we're making a map. That's all that's all the Smith chart is. It's a map. It's this like the same thing you when you walk in the mall and it says you are here and you want to find Radio Shack. You know which aisle to walk down. That's all this is. So if it's as we've drawn it here, to the right of 0 is a resistance that's higher than 50. That's all that means. And if it's to the left of the bullseye, it's a resistance that's lower than 50. 50 is the bullseye.
Got it.
So if you plug in some real numbers, let's just make up an imaginary number. Yeah.
It's a done deal now. Anyway, let's make
Okay.
up an imaginary number.
Yeah.
Of resistance.
Yeah.
Uh,
Pull a number out of the air.
32 ohms.
Okay. So 32 is going to be to the left or to the right of the bullseye?
We are going to be to the left of the bullseye, somewhere
Yep.
around here.
Yep.
Yeah.
Why don't you put a dot there?
Let's put it. Yeah.
Great. Okay. Now let's pick a J factor. Is it going to be in our imaginary antenna? Are we going to be inductive or capacitive, and how much?
We are going to have a slightly capacitive antenna.
Okay.
Probably measured in picofarads typically.
Yep.
Yep. And zeros the target. So
Yep.
we're gonna have a positive number of capacitive. No, that's
No, it's a negative, and it's going to be measured in
negative
J.
number, and it's gonna be measured in
J is just where is it on the map? That's all this is. It's not an actual value.
All right, so we're gonna be slightly capacitive.
Yep.
So what do you want to do? You want to put a
So write down. So lose the 5. You've got 50 ohm here under R. That's fine.
yeah, I'll
So
lose it.
on the red dot, I would make on the left-hand side 36 equals R, just so that we know what that dot represents. Right. And then the next line, put J equals, or some number equals J, whatever number you'd like. It can be a positive number, that'll be inductive. It can be a negative number, and that'll be capacitive.
J equals negative 14 puff.
Okay, just for convention. No, it's not going to be puff.
No.
Just like 36 isn't necessarily ohms. It is in, I'm sorry, I'm getting confused. I'm confusing everybody here, including myself. But It's a location on the map, really.
Okay. All right. It would be okay. So J equals -14, or
Okay,
negative 14
-14.
equals negative
So,
14
yep,
equals J.
yep.
Okay.
Okay. So, um,
Oh, these are
so
small for you. I'm sorry.
that's okay. I can see it. So if we know that J0 is where the purple and the green line intersect at the bullseye. That's J0. So try to figure if 36 is that much to the left, 14 is going to be down,
Just
and
a hair.
yep,
Yeah.
and put a dot there.
I'll do it. Here's a dot.
Okay, except that it's going to be on the purple line, just like the R is
Oh,
on the green
absolutely on
line.
the purple line.
Yep,
Correct. Okay.
yep,
Sorry.
great. Okay. So now what you want to do is take that triangle and flip it. And I know we really can't. So let's do it this way. We kind of painted ourselves into a corner.
Well, I mean, I could just do that.
Mm-hmm.
Yeah. Maybe change the color first.
Yep.
Something like that.
Yeah.
Okay.
Okay. So I think I may have led you down a wrong path here, and even though I had good intentions, but because I'm seeing a potential issue with this.
Okay.
The issue is this, that the triangles are straight, which is great, but the Smith chart is a circle. So those straight lines on the Smith chart are really curves. They're not straight lines. So I messed up. What I should have done was can we get rid of the circle and the green and the purple line? We'll go to that in step 2. I actually skipped a step.
I have a tool for this.
Okay.
You want to get rid of this circle?
Yeah.
Bam. Whoop.
Great.
I got rid of everything.
Yeah.
Okay. We can fix it from here. I think. What what you ooh. What you thinking?
Well, if we started with just that triangle again.
Okay. Triangle. Let's draw a triangle. From here, from the center.
Sure.
Okay. And this is going to be the extreme edge. That means that we're going to end up somewhere here.
Yeah. That's
Okay.
okay. Yeah.
So let's get a black. Oh, that was heavily delayed. So is it going to end here on the circle?
Yeah, but it doesn't have to, because it's not in this part of the lesson. It isn't about the Smith chart yet. See, I skipped a step. I combined the two too quickly. So that's on me. That was my mistake.
Is this better?
Yeah.
Okay.
Okay. So let's also, if you humor me, let's change the 36R
Mm-hmm.
and instead make it something larger than 50. And that will follow our triangle the way that
Oh,
it's
because
drawn.
we're right.
Mm-hmm.
Okay. 75.
Magnificent.
Okay. Let's Oh, that's how you adjust the size of your tool. Blimp. Guess we can kind of clean up the rest of this a little bit. I don't think we need. We'll keep that just for reference.
Mm-hmm.
Anyway, and we are going to. Our resistance is going to be 75, right?
Mm-hmm. Yep.
Okay. Let's get rid of these point circles too. Let's fill these in with white. Blink. Oh, that's black. That's white. Oh, how magic is that? I mean, you click white, you get black. What in God's green earth? All right. Well, anyway,
Hmm.
it's Windows, folks. It's a Windows product.
Mm-hmm.
All right, let's get rid of these like they never happened. Let's go 75 ohms, and that's going to put us no, I'm sorry, resistively.
Yeah.
Hold on. Yeah, resistively 50. Now we have 75 ohms, and this is a 50 to 100 scale. How do we interpolate the maximal of this?
Okay. So the
But it's all relative, right? It all
you're
scales.
right.
Okay.
Exactly. It's
Okay.
all relative. So you can make the outer edge of the circle any number you want. Let's keep it simple. Let's say it's times 10. So it's 500 ohms on the outside. It's really infinity, but just to keep it simple, let's say that the outside is times 10. It's 500. It's 50 in the middle.
Oh, okay. So 75 would be about
Yeah.
anywhere close
It's
to here.
it's okay. It doesn't have to be dead on. It's
Okay.
okay. So now we're going to pick a J, and it's going to be a positive J, the way we have it drawn on our triangle.
Okay. And we're going to be slightly inductive a little bit.
Yep.
Okay.
Okay. So let's see. So actually, that circle that's on the J, the inductance part, the purple,
Mm-hmm.
put that on the triangle on the vertical line. Just move it all the way over to the right,
Let's see.
or redraw that red. Yeah, put it about halfway up, just so that we get a.
Yeah.
Okay. Move the R1, the 75. Put him in the middle of the red line.
Right here.
Yep. Yep.
Okay. Not a problem. Uh, I guess I need a lesson on paint now. Okay.
Okay, great. So um so we know that we're so much over to the right. That's our R, and our J is up. And if we drew a not a connecting line between the two red points, but take the red line on the right, and if you made a horizontal line, and then you come down at a 90 to the other red one.
Come down to a
Now
90. Oh, you're talking
take
about here.
yep, and then stop and draw straight down. Yep,
Oh,
right.
okay.
Okay. Where that takes a 90-degree bend down, that edge right there,
Yeah.
that is the spot on the map where those two numbers line up. So if you were to write the complex impedance, if you were to write it this way, Z equals 75 plus J 100. I'm just pulling these numbers out of the air just to
75 plus J100, huh? And let's do this. 75 plus J100.
right.
Okay.
That would be where our yellow dot is. It's so it's 75 ohms on the R, so we know that it's to the right of center at some point along that line. And the plus J 100, the plus means it's above the equator. If it was a minus, it would be below the equator. So it's above the equator at some value, and the value is 100. So we go up 100. And where those two lines up intersect, that's where the yellow dot is. And all that means is that's the location on the Smith chart. Again, it's just think of it as a map. It's you are here and you want to get to the bullseye. Okay.
Mm-hmm.
So if you think of it that way, if we're at the yellow dot and I want to get to the bullseye, I need to go down in resistance a certain amount, and I need to go in a negative J a certain amount. And then those two numbers will resolve. If I have a positive number and I add a negative number to it, the net result is 0. And that's the J0. So that's, I really went down a rabbit hole and I probably shouldn't have, but
No, this is
that's
great.
okay.
Having a great time.
But that's, I guess I'm answering two questions at the same time. So the Smith chart is a map. It simply shows you what you have, what you're measuring at the antenna, at the load. That's the spot on the Smith chart, on the map. And the center bullseye is what do we have at the transmitter? And we're trying to match those two together. That's all it is. That's all the Smith chart is.
Yeah.
The triangle part of it is to show you that the R, forget about Smith chart for a second, just look at the triangle, the black triangle.
Mm-hmm.
The R is the horizontal line, the J is the vertical line, and the Z is the hypotenuse. So if you were to write down the Pythagorean theorem, which is a squared plus b squared equals c squared, that's what this triangle is doing. So it's a squared if you want to type in the box there. And it may not give you a squared.
Yeah, I'm not
Just
going to be able to pull that one out real quick. It's okay.
How about
I can draw it in after the fact. A squared plus b squared equals c squared. And
right.
I can just simply put freehand me a little 2. Ooh, boy, that's rough. A squared.
Yeah, this is tougher to do
on a mouse.
Yeah.
I was looking at something I drew with you the other day, and I was really impressed with myself.
Yeah,
I
cool.
was like, "Wow, that one turned out really good."
Cool. Yeah.
Anyway,
so the bottom horizontal line is the A part of the equation.
right.
The vertical part of the line is the B, and the hypotenuse is the C.
And this is where you get your C value.
Right. Right. So if I go over on the A a certain amount, in this case it happens to be 75, and the B is a 100. So 75 squared plus 100 squared equals C squared. So that's all we're doing. We're just filling in the numbers for whatever those letters represent on the map. So I can't do it in my head, but if you want to bring up the calculator,
Sure.
you can go 75 either 75 times 75, or you can hit the x2 right under CE.
Yeah. So we'll go 75 squared.
Mm-hmm.
Plus.
Okay. So write that number down.
Sure.
Put that on the
Well, I don't know what
page.
I've done. Let's go back. 75 squared is 5625.
Yeah. So A is 5625, right?
It's these big numbers that we were
Yep. Yep.
just looking at just a second ago.
Yeah. Now we'll do B.
Oh shit! I've got one of these keyboards where the damn Alt key is a command key
Yeah.
and not a proper Alt key because it's a
Yeah.
it's a operating system fluid keyboard. Oh, I had it up. And now we're going to do 100 squared.
Right.
That's 10K.
Right.
And we're going to add these two numbers together.
So write down on the left, write down B equals 10K.
Got it.
Perfect.
Okay.
Okay. So now, no, it's not squared. It's it because well,
no.
okay, yes, it is. Yes, it is. You're right.
B
You got
squared
it.
is, yeah.
Yep. So add those two together and write C squared equals whatever that value is that you come up with when you add the two together.
15,625.
Mm-hmm. Mm-hmm.
Okay.
Okay. Now the fun part. We take the 15,625 and we get the square root of that.
Oh, Lord. Give me my calculator, Windows. What have you done with my mouse? All right. I'm sorry. We've got this number.
Yep.
Okay. And
So
we were going to.
it's under the C. It's the square root. Yep. And that's your answer, 125. So C, not C squared, but C equals 125.
Okay. So squared equals 125.
So it's C equals 125. Right.
Okay.
That's it. That's our definitive answer. So 75 ohms with a J of plus 100 is a total impedance because it's a combination of the two. And the
Right.
answer is 125 ohms. That's the C.
And that's why my 75 ohm cable at certain points exceeds 100 ohms.
Yep.
With a 50 ohm load.
Yep.
Yeah, and that's where the 2.2 swir comes from when I match it to a high impedance load, or when I match it to a high impedance curve.
Right.
Yeah. So, for example, here. 112. Close. But that's Z equals 112 minus, anyway. Probably going a little
Where
farther.
where do you get the 112 from? I didn't see it.
Sorry. Okay. Right? Wait. Oh, I'm blocked. Sorry. Let me get me out of the way here. Down here at the bottom.
Ah. Oh,
Oh.
okay. It does give you the Z. Right.
Yeah. And if you click it, it cycles. Okay.
Right.
Gives you all or nothing. It's almost like it's a teaching tool. You can hide certain values.
Oh, it is. Oh, yeah. It's a great program. Yeah.
All right. So
that's what the Z. That's what Z means. Really, it's a combination. It's not because a lot of people look at it and they go, "Well, you just add the two numbers." No, you can't. It's A squared plus B squared equals C squared. That's where it comes from.
Okay.
But and the electricians, they use the same thing. They do it, it's called power factor. Instead of um, instead of calling it SWR, it's a power factor. But it's basically the same thing because it's still an oscillating current. It's not DC. RF
Right.
is AC, just a much higher frequency. Hey, there we go.
Yeah.
So, in answer to your question, I know we went down a rabbit hole here, but
No, that's great.
because your question originally was, which number do I use, the R or the JX? Can you answer your own question now?
JX.
No,
No, why?
it's a combination of the two.
Oh, these two make up
Yeah,
our Z
you get. That's it.
right
Yep,
here. And it
yep.
shows, in fact, it shows both of them. And it shows one minusing the other.
Uh,
Six
it isn't
25.
minusing.
No, it's
No,
a
what?
negative. It's a negative. I'm sorry.
Yeah, it's saying that the J is a negative number,
Yeah, it's not a
but it's not
perfect.
giving. It's not giving you the Z. I know it says Z in ohms, and this is misleading. It isn't because I can't really see what the numbers are. They're small and they're gray, but it looks like the R is 6624. Is that right?
Correct.
Okay, and
I can
the
probably adjust
that's
my
okay. You can leave it. It's
resolution.
fine.
Okay.
The
All right.
the J is minus 6196.
Yes.
Okay, it isn't 6624 minus 6196. It is 6624 squared plus minus 6196 squared. You add those two together, and then you take the square root of that
Those two.
combination, of that sum.
So let's
And
practice it.
that is the Z.
6625 squared. Whoa, hey,
Mm-hmm.
let's clear this out. 6625 squared. Oh, geez.
Mm-hmm.
I'm supposed to square that number? Really? Okay. And then
Uh-huh.
we're going to add a negative 6197 squared.
Yep.
This is getting fun fast. Add
Yep.
a, well, I can't, I need to add a negative.
No. No.
No?
You gotta take you gotta take a negative 6196 and square that.
6196
It's a
negative
negative though. Yeah.
squared.
Right. So you take that number and
Ah,
you add it to the first one.
now I can add the square of 6625.
Mm-hmm.
And now I have this. I need the square root of that.
Right. Yep.
Bam.
Yep. And that's your Z.
Okay.
That's the correct answer. Except I don't buy it because it's exactly the R.
Hmm. No, it's not. Look,
Oh,
6624,
okay. It's 1 ohm different.
6625. We might have done something right. It looks like it. Too close to call. It's within the margin of error.
Yeah.
But but the first thing I see is a swerve 248,
Mm-hmm.
right? And so I love I love telling this to new hams. Don't look at the swerve. Don't just forget about it. Even though we're gonna totally use swerve for the rest of our ham career, but just stop looking at the swerve because that's just a presentation number. Um, when I see this high swerve and what I've drawn here, because I am in feeding it, I'm
Right.
not accounting for pushing impedance into this wire. And within this software, there's a place where I can add that, and I've done it before.
Mm-hmm.
And that's going to be, let me guess, probably going to be in the, oh, damn it. It's going to be up here. It's going to be, I think it might be an element edit or HF components. Here it is. and there's going to be a place where I'm going to see 50 ohms somewhere here because it thinks that there's a 50 ohm load right here, the feeder.
Mm-hmm.
Well, can I just change this to my high impedance transformer number or no? I don't
No,
think so. That's feed
because
line.
this is creating an L match.
Okay.
This is trying to match 50 on the left to our complex impedance on the right.
Okay.
The SWR, by the way, the 248,
Mhm.
it's if you take 248 and you multiply it by 50, you will end up with the 6625. Well, you should. Yeah, see, that's why I don't think we did our math right. Because the 12,000 should be our. Let me think about this. What do you end up with? 248 times 50?
248 by 50.
12,000.
A lot.
Well, I don't know that I buy that either. I mean, that should be right. Yeah, I don't know. I didn't do my homework, Teach.
It's okay. It's okay. We can come back to this.
Yeah.
Yeah. How do I tell the software that I have a transformer connected to the feed point?
Oh, I don't know that this software will let you do it, but we can try. So if you hit cancel on that pop up there,
Sure.
bottom right, or yeah, okay. And if you go to where is it? Setup
Mm-hmm.
at the top, and then you click on setup again. And on the left-hand side,
Oh, there it
says
is.
standard. Yeah, there's a pull-down
Yeah.
menu, and I don't know that it will let you. Yeah, it'll do 600 ohms.
But I can do.
You can try typing in a number.
Was it 2650? I forgot already.
Yeah, it's in that ballpark. I mean, 50 times 49.
Looking in the chat here, somebody said it. I could use a calculator much faster, Alan. 26. No. 50 times R49 to 1.
Mm-hmm.
2450. I was
Yep.
close.
Yep.
2450. All right. And the
So
OK button.
that's now the output of the transformer.
Okay.
So we're telling Manigal that this is the output of the transmitter. It isn't, but we're fooling the software. So now the SWR
Has
is
dropped
going
to
to
5.
be the match between the transformer and the wire.
And of course, nothing has changed here.
Right. It won't. Yeah. Right.
No. This is much closer. Way much closer. Now, how do we fine tune that? I guess I would need to look at our new values here. Or maybe I need no, it's already rerun it for me.
So what I do is I change the frequency.
Oh, that's right. The
'Cause
frequency is the
it's
easiest way
just
to run around.
yeah, and you can
Let's
just
go a little higher.
yeah.
And no, it's lower, which tells me we have not enough impedance. So let's go back to the frequency we were working on, and let's go. Whoa, my God, Ziggy. Set up. Let's make it, I don't know, 2700 ohms. And I've gone too far. So I was at 2450. Let's just make it 2500 this time and see if it's dropped from a 5 swear. No, I've completely messed up.
So what I think you're looking at is the column that says SWR.
I am.
Okay.
I don't think I reran it though. I'm not. I think it reruns it when you change this 2450. was what we did before, and we
Yep.
should get. Now I'm getting a 20 swir. No, oh, you got to rerun it after you do it. Ding dong. I thought the flash meant that it was recalculating. No, it's just refreshing the screen. 20. Let's do 2,500 ohms, and rerun it. Swir didn't change at all, not even a decimal point.
Yeah.
Okay.
If you look at the J column,
Uh-huh.
those are all big values and they're minus. So it's you got 6,000 ohms of capacitive reactance. That's what that number means. It's a minus, so it's capacitive, and it's roughly 6,000 ohms. Okay, so it's trying to stop the flow of the RF going down it. So ultimately, you want that J to be 0. That's the target. The R can be 6,000, but you want to get rid of that J. So,
Okay.
so because it's capacitive, let me think about this. If it's a half wave, it flips it. If it's a 90 degree, if it's a quarter wave and it's too long, it becomes inductive. If it's too short, this is just a quarter wave. If it's too short, it's capacitive. When it gets to a half wave, those two flip. It's the opposite. So for a half wave, if it's capacitive, that means that the antenna is a little too long. It's the exact opposite of
It
what a
is too
quarter
long
wave
right
is.
here. I see
Yeah.
a little bit of current mismatch going on right
Uh-huh.
there.
Yep.
So you
Yep.
said the easiest way to fix this is mess with the frequency.
Right. So
Okay.
if the wire is too long, let's
So
lower the
lower the
frequency.
frequency. Yeah.
Right.
Let's go maybe 3/4 and see if that's a little closer. Hey, a 1/6 on the
Bada
swerves.
bum, bada bum.
Let's look at that. Oh my God, the current has just
There we go.
completely shut off this
Yep.
thing.
Yep. Yep.
It's off the chart.
Yep.
What have we done? Are we still filling it with 2,500 ohms? We are.
Yeah.
Let's
While we're doing this, I'm gonna see if I can find a picture because it will show that
that
what I
was like
just said.
double the current coming out of this thing,
Yeah.
Hollywood.
Yeah, because you got rid of that 6,000 ohms of resistance. I think the last I saw it went down to 400
I'm sorry.
in change, right?
Down to 400.
I'm
My
actually looking at a different
word.
screen right now, so I can't see what
You know,
you're presenting, but that's okay. But that's the key is to lower that J.
three. So we have a positive number this time. That means we've gone just a click too far.
Mm-hmm.
Maybe? Yeah. So let's go
Yeah.
3, 4, 5.
Yeah. And
Nope.
you will see that a very small change in frequency or a very small change in the length of the antenna will make a enormous change in the
Yeah.
J. It's really touchy. And that's what I've been saying all along, that a half wave, it's like trying to balance a pencil on the tip of your finger or a yardstick. Doesn't matter.
I
You have to keep moving your finger. And any little change, it wants to fall over.
Yeah, well, I mean, I did technically by putting a 1 here, we're technically sliding like what's that? Hundreds, 10,000ths. How
Yeah, it's
many?
a very small
Very
amount.
yeah.
Changes that J radically. It's like it
3,
falls off of a cliff.
405. Nope. Wrong direction. 3, 9. Hey, 290. Getting closer.
Mm-hmm.
3, 9, 3, 8. Oof, getting dangerously close here. 3, 7. Oh, too far. 3, 7, 5. 36. The swears aren't around 2 anymore, but the JX is lower.
Yeah, if you, yeah, the JX, if you get that as close to zero as you can, but I mean, don't go crazy with it, because
Right.
any little change is going to make 100 ohms one way or the other. But going from 6,000 ohms to 400 ohms was a huge change.
The
And
the current here just blows me away. Again, we're off the chart again. We've gained
yeah,
even more current.
yeah, and that's the goal,
Oof.
is to get as much current flowing in that wire.
That's so strange. I'm so glad that you brought that to my attention, because we've now completely utilized
Mhm.
the counterpoise,
Mhm.
all
Yep.
6 feet of it,
Yep. Yep.
for this one frequency. What let's see.
Boy, I've got so many pictures in my head that I want to share, and I don't know where they are in my computer, but I know that I have them.
375 times 2. Should we dare push 675 on this? Is it even
Yeah,
that
you're
way? Am I on the
uh
right path?
uh let me see what you're
That's
doing.
double of the frequency that we were just working with. We were at
Yeah,
3.375, and
yeah,
then double of that would be
yeah,
6.75.
yeah,
We're free banders here, kids.
yeah.
Buckle up.
Ziggy, play with that for a minute. Let me see if I can find, because I'm
Oh
trying to
yeah.
do three
Yeah,
things at
it's
once here. So I'll hang
it,
with you audio wise, but
it's
let me see if I
it's
can find this picture.
it's damn near perfect. Swords is up just a little bit, but Ape's down here in the comments. So I'm sure he's pulling his hair out on me. Sorry, Ape.
Jump in.
Yeah.
What I'm looking for is, I have a beautiful map um, that shows the different lengths of antenna, different heights, electrical lengths of the antenna, and how does it affect the capacitance and the resistance and the inductance. And it would be cool to put that on the screen for reference, if for somebody viewing it in future.
hmm This is an interesting topic. The current never falls to zero between the two half waves here,
Right. That's right.
and that's why you get a little bit of. I need to stop saying flyback, but I just love referring to swir as flyback.
Mm-hmm. Mm-hmm.
And then 675 times 2 again. It's just going to get worse and worse. Times 2 again. That's why there's no
Ooh,
such thing.
guess
Yes,
what? I found it.
of course.
I
13.5.
found it.
Hey,
Hallelujah.
hey, 3.5. The show just got interesting, folks.
Either that or everybody just went to bed.
Mm. Oh, we've got 9 people hanging out with us.
Cool.
Yeah. What was the swir on this? Yeah, the swir is gradually increasing.
Yeah,
Like
it
the
will. It
JX
will
out.
it will repeat, but it will also have more losses, because the other thing too that's a little bit misleading with the software, we have to remember that these humps are current,
hmm
that were the blue line.
Yeah.
The problem is, the first hump is going in one direction. The next hump is going in the opposite direction. They're not all facing the same direction, because the RF is alternating current. It does a half of a cycle and then it flips. It's the same amount of current, but it's in the opposite direction. So if this was on the fundamental frequency and it's a half wavelength long,
Mm-hmm.
now there's only one blue line from start to finish. There's only one hump. It only goes in one direction. But if you transmit on a harmonic, let's say it's the second harmonic, there will be two blue humps. So there's two half waves and they oppose each other.
That was at 675, 675.
Yep. It doesn't see it. It's the way that the software is displaying the image.
It's
All the blue line further away from the black wire, all that blue line is the amount of current. It doesn't show you the direction of flow. So you have to understand in your head that it's starting off, it's going, let's say, clockwise. It starts at 0, it goes up to a peak, it comes back to 0. Okay. And then it flips. It goes the opposite direction because it's really a sine wave is a circle cut in half.
I see what you're saying here. Give me
Right?
some paint. Let's see here.
Yeah.
Let's save this one. There's a bitmap. Let's throw this in the Hollywood folder. And let's see if I can't do this the smart way. Maybe not. Control Z, that's okay. I'm not trying to impress anybody tonight. Why doesn't Control Z work anymore?
Because it's Windows 11.
I'm telling you. I want
one step forward, 2 steps back.
I throw it all away. No, I don't want to save it because you don't care either. Yeah. So in 1 hertz pass, we look like this, and in the next hertz pass, we have the inverse.
Right.
Yeah.
Because it's really a circle. So you're a mechanic. So think of crankshaft. The crankshaft is rotating. It starts at 0, and it goes halfway around, and then that's the first half of the sine wave, and then the second half, still going in the same rotating direction, right?
Yeah.
Yeah.
Yeah, energy was applied, and now energy giveth and energy taketh and cometh back again. Yeah.
So all that blue line means is the amount of current, not the direction of flow. And that, believe me, that tripped me. That's why I bring it up, because that tripped me many, many, many times. I looked at it and I'm like, why is it doing X, Y, and Z? Why is it behaving this way? And I'm like, oh, duh.
So this whole time, I don't know why I don't have my little handy dandy. This whole time I was imagining that it was doing this.
Sure. Yep.
That I was getting these circular lobes. These balls basically of radiation. And that's not necessarily the case at all.
Except that, you've got a good point, a good theory. What happens though is, let's go down that rabbit hole just for a second.
Sure.
If I have, let's look at the first circle. So the red is our wire, and we have current flowing through the first circle, the top half of the first circle. If I were to have current flowing in the bottom half,
Okay.
If I were to have current flowing in the top half and the bottom half,
It would be destructive.
yeah, right. They
Okay.
cancel. Exactly. And that's true for any of those four circles. So what's really happening is you're having current flow from left to right at the start, and it goes up the first half of the circle and then down the second half of the circle.
Boy, that's the way to make a sine wave, isn't it?
Mm-hmm. Mm-hmm. Yep. Yep. Exactly. That now is the direction of flow of the current down the wire from the transformer to the end of the wire, left to right. But when you look at Managal, it doesn't show you this. It doesn't show you that. It shows you that there are two humps and they're both on the top, but they're really not. See, that's why it's misleading. The blue is just the amount of current, not the direction. The direction is below the wire. It's going in actually in the opposite phase.
Yeah, I've always thought about that. I was like, what?
Mm-hmm. Yep. It's
I know
tough
the
to
current's there, but
conceptualize.
the current's there, but where?
Yep.
How to see?
Yep. Yep. It's just like, think of it. Maybe it's easier if you think of it in DC. If I have two batteries, I have two car batteries. If I put positive to negative, I end up with 24 volts from the total battery pack. I get two 12-volt batteries, right? And I connect
Yeah.
them in series. So in the middle, it's the positive and the negative are jumped together between the two. Battery A's positive is connected to battery B's negative,
Yeah.
right?
Yep.
So I end up with 24 volts total. But if I were to flip battery B backwards, in other words, I have a direct short. Battery A is feeding into A is feeding into B and B is feeding into A. I have a circle.
Oh,
If I put a meter across the two batteries and they're both exactly 12 volts and they're equally charged, I get
there's
0 volts. They cancel each other out.
there's
There's no,
there's current, but there's no voltage.
yeah, but right. Right. The two batteries are self-destructing. They're feeding
Yeah.
each other end to end. But if I put a light bulb across the two of them, I get 0. The light does not light up. So,
Liberty Liberty Cave's
okay.
got a question for you.
Yeah, sure.
Isn't the magnetic
Well,
component
yes
90
it is,
degrees out?
Liberty. Yeah, yes it is. All I'm doing is I'm overly simplifying it just to show Ziggy the direction of the flow of that current. But yes, you are right. That's Eli the Iceman. That's if it's inductive, the voltage is before the current.
I'm saving this damn sine wave.
Yeah, yeah.
For next time.
Let me show you a picture because this
Absolutely.
may help. I hope it does. Let's see. I go here, and I go no. I go on the plus. All right. Share the screen. One entire screen. Yep. Yep. Okay. All right. You see the picture?
I do. I wanna show just you. Let me see.
Okay.
Hey.
And I have a second one that's very similar to this. If this one is confusing, we can try the second one. But I think this will explain it. Okay. So here at the 0, this is our transmitter. We're starting at 0. If I go to the right towards the load, the antenna, and the antenna is a quarter wave tall. It's 90 degrees. The antenna is connected. It's a whip that's connected directly to our. There's no coax. There's no transmission line. The antenna is the thing that's screwed into the back of the radio.
The way God intended.
Yeah, and it's a quarter wave. It's a 90-degree quarter wave. So that's why they say quarter L. Okay. Look at the X. X is the same as J. It crosses over the zero line. So it has zero reactance at that point.
A maximal and a maximal load of resistance as well. I see R is at a peak at that point in time.
Okay, so yes, it's a peak. It's actually
above where you were.
This is misleading a little bit here. Let's do it this way. Let's okay.
Forget I said anything.
No, you're fine. You're fine. I screwed up. Let's forget what these numbers say, because this is misleading. Our transmitter is here where I'm circling.
Okay.
If I go a quarter wave away from it, that's here. The X crosses over the zero line. So there's 0x, and there is a low impedance. This is R. This is low impedance. This is 70. This is a 90-degree quarter wave radiator. If it's a half wave, this is my transmitter again. So I go a quarter, and then I go another quarter. This is now a half wave.
We're back to where
high impedance also crosses over the X line. So it's resonant, but it's very high impedance here. And if it's a 90-degree quarter wave, it also is resonant, right? But it's low impedance now. So
easier to drive.
So there's two takeaways here. Look at the curve of the R. See how it's a nice shallow dish, whereas this one is a peak. It's a sharp peak.
Mm-hmm.
Okay, so you can see that this one is a lot less stable than this one. If I put a marble here, it's going to find the center and it's going to sit there all day long. If I put the marble here, it's going to fall off one way or the other. Right? It's not stable at this point. This is a high impedance. This is low impedance. That's why I've always used the term. A quarter wave radiator is like grabbing the pencil from the eraser and picking it up off of the desk. It's very stable. Okay, but if I use an end-fed half wave, that's this. Now it's a very high impedance and it's unstable. It's like balancing that pencil on the tip of my finger. So here's the other takeaway too. The other takeaway is, yes, it's resonant. So this is a half wave. It crosses over. It's resonant. But look at how steep this curve is, the X curve, compared to this one. Remember, this is the 90-degree quarter wave. This is the end-fed half wave. So any little change in the length to the right or to the left will make a big change in the X and also a big change in the R. But if it's a quarter wave, a little bit left or right makes much less change in the X and almost zero change in the R. It's very, very stable.
This is why your quarter wave has an unbelievable broadband characteristic.
Correct. This is low Q. This is high Q. Bingo. You got it.
Sometimes they're too broadbanded.
Yeah.
You go, now wait a minute, somebody's lying to me.
So if you make a dipole and you feed it in the middle, each side of center
is a quarter.
Is this. Right. Real easy. And if you take the same piece of wire, but you don't feed it in the middle, you feed it at the end, you end up with this.
Now you have to learn how to juggle and ready.
Right. It's still resonant. It still works, but it's a bugger to get it lined up perfect. It's a moving target.
You know,
If you go a foot above the, a foot higher in the ground, or the tree moves, then this electrical length moves a few degrees. It's right on the edge. It can be done, but this is easier. And
I,
that's why we always start with a dipole. When you have somebody starting out, you say, build a dipole first, because
yeah,
it's easier.
it's like riding a tricycle.
Yeah, yeah,
You're not going to
yeah.
fall over as easily.
And that's it kind of segues with what you were saying with Frank earlier tonight, is that high expectations. I see this a lot with advertising. We it's very easy to start with a 49-1 and you get a half. That's this. You're almost setting yourself up for a mess.
I can't tell you how many
If it's your first
hours,
antenna. Yeah.
hundreds of hours I've spent out into the field just
Yep.
building character.
Right. Right. But you see,
because
but you're
because my
you're
in-fed obsession has definitely let me down a lot.
yeah, but that's how we learn. But that's okay, because
Yeah,
this is not your first rodeo.
no.
See, if you had just got your license yesterday, and I were your neighbor, and I said, "Hey, let's get on the air," and you start with this half wave end fed, you
Mhm.
might get all frustrated with it. It
Absolutely.
may work right out of the box, but it
Eh,
also may not work.
it may work if you get one of these trickery do
Yeah,
in feds. Who was it? Jim and Ape. They both got this Chinese infed
right,
transformer,
right.
and it was on a green core. You
I
saw it?
did.
Um, did you see Jim's video at the end where he showed the SWR suite for 80 meters?
Yes.
Holy hell! I've
Yep.
never seen anything like that in my entire
Yep.
life.
Yep.
And I'm like, there's only one way you can do that.
Hmm.
The RF staying in the
That's
core.
correct. It's lossy. Right. Right. This is this is what's on the wire. This is not what's in the core. The core just tries to match to this.
I tell everybody that uh, there's three different views. There's the view of the coax. Throw that away. That's not what we're talking about. There's the view that you see into the transformer, and then there's the actual what's going on the wire view, and then these lossy cores, they hide the
Right.
wire,
Right.
right?
Exactly.
Yeah.
So
So you don't actually know
this
what's
is
going on.
this is the
Oh, this
same.
is
This is
awesome.
the same,
Where did you
but
find this
different.
gold?
Okay. So let me
Okay.
see if
This is our matching components
well,
doing their work through the phase.
sort of, not quite yet. So this is the
Okay.
same thing. So if I'm here, this is my transmitter, and I go 90 degrees away from it, so it's a quarter wave. I can't help it. We think like engineers. It's 90 degrees is a quarter, right?
Right.
Okay. So what do I have? I have low resistance, and um, L and C cancel out. So it's resonant at that point. So you see that the X, this is a big C, it's a big X, but it's saying it's capacitive at this point,
But it's mostly
and it gets less capacitive, less
right.
capacitive, neutral. They cancel each other out, and then it becomes inductive, L, and larger L. And what this is saying, these schematic symbols, is when it's at resonant, it acts like a capacitor and an inductor together in series. They cancel each other out, and what you end up with is just the pure resistance of the wire. It's called the radiation resistance and some losses. But these two cancel. That's the bottom of this dip. If it's too short, it's very highly capacitive. If it's too long, it's inductive. This is, again, working the opposite. We read left to right, but in this situation, our transmitter is here on the right, and we're
Starting at
reading it
0,
to the
kids, on
left.
the right.
Right, right, right. So at a half wave length of wire, I'm now here. See, lambda over 2, half wave. So it's a very high resistance. The R is huge. And on one side of the R, the L is very large. And on the other side, the C is very large. And right in the middle, they're at resonance. But it's a cliffhanger. And the schematic symbol for that is this. This is a tank circuit. So they're not in series like they are here. Now they're in parallel. And so it is a
Competing.
high impedance, right?
Yeah.
Right. This way is low impedance when they're in series. When they're in parallel, it's high impedance. And this is also what's happening inside the tuner too. But that's another thing. Keep it simple. So if you just look at that curve, you can see what's happening. Now my doublet is too short for 160. It's 150 feet long.
Okay.
So
Exactly 150?
yeah,
I'm going to model that.
yeah. In fact, I already have.
Oh,
That's it. Let me show you. Yeah. Let's get rid of that. And let's go. No. Let's go to this one. Aha, there it is. Because I was looking at it earlier. Now I have these two red dots, which are some loading coils. So let me make those go away. And this is Hollywood's antenna. So I've drawn in the balanced line here too. Um, if I hit it with 160, okay, that's what I end up with for a curve. So it's not long enough. We can see that because it's not a nice circle. Yeah. And I can also see
your feed,
look at
your feeder is playing a massive part in this.
Yeah. It's already low impedance here where it's feeding it, and it gets lower still at the transmitter. And so what I end up, look at 2 ohms. That's what my transmitter is seeing.
Ouch.
And it's highly capacitive, very highly capacitive. But you know what? That antenna still works. As
you
long
can still
as
load it up on.
Yeah. If I can match it, if I can use a transformer backwards. Okay. So I go 50 down to 2 ohms. It does satisfy that equation. And I can put, if any antenna, and this is the key that I'm trying to say here, any wire, I don't care how long it is or how short it is, if I can get it to accept power, it will radiate. It won't radiate quite as efficiently as a full-size antenna, right? Because this antenna is too short. It should be 260 feet long, but it isn't. It's 150 feet long, but it still works. It doesn't work as well, but it still works because that's all the real estate that I have. So at the end of the day is use what you have. That's I guess what I'm really trying to say. Now,
these loading coils.
Yeah, let's go back to that.
Yeah.
So here's why I did it. Here's why, and they're ugly as sin. The loading coils are. I took 2 plastic, 2-liter bottles, and I simply put I put a couple of holes in them, and I wrapped the existing wire that's already out there on the doublet, and I went 5. I just picked a number out of the air. I went 5 times around, and I put a couple of tie wraps to hold it in place, just as an experiment to see if it would follow what the model was telling me that it would do. So let me show you why I did it. Let's shut these off, and then we'll go on a harmonic. So we'll go up here to 28.
That's what I've learned is that inductors out there on your wire are actually very forgiving.
Yep.
As far as their construction.
Yep. So these are not traps. They are just inductors, but this is without the inductors. This is what I had last month. No induction, just the wire. And so you can see from the transmission line, by changing the length, I can change the impedance that the tuner sees down here.
Is that right out the window there?
Yeah, it goes. I drilled 2 holes in the outside wall and the Romex wire, I have 2 wires separated by about 4 inches. That's my balance line. It's all homemade. It goes right outside the wall. Boom. So
Just like in the old days.
yeah,
Right
yeah,
through the wall.
yeah.
Love it.
So each of these blue humps is current. Again, it doesn't show you the direction. It's just the amount. And at the end of the day, I get this really ugly pattern. And yes, it radiates, but it's acting, let me go here. It's acting like a beverage, which is not a bad thing if it were pointing the right way, but it isn't.
Mm-mm.
So the way I have it configured, and again, you can see the bend in the.
Oh wow, you
Sorry,
even
I'm
have the
jumping
asymmetry
here, but
of it.
yeah, it really looks like that. If you were a bird flying overhead, it looks like that. It's not a straight shot because I have it.
Okay.
I'm lucky. I have my neighbor's tree here, and I have my property here, and then this wire has to go over a bunch of trees. It's actually touching the trees. It's a sin. It shouldn't be that way, but that's all I like to work with. And it goes into the swamp, away from the house. So the angle here, this line, this blue line, is facing Africa. Okay, from the Cape. So in the opposite direction, it's probably going up to Washington State, somewhere in that vicinity. So it's so this way would be southeast, and this is northwest, or north by northwest, maybe. Okay, so so this is what I end up with for a pattern on 10 meters. And if I want to talk to the US, that's behind me. That's this way where my pointer is. I get very little signal there. All the signal goes down to South America, which is fine. And this one maybe goes to England, which is also fine. Or maybe just short of England. But I'm not feeding Europe. Europe is over here somewhere, and I've got nulls.
Boo.
Okay? So I can't talk to the US and I can't talk to Europe on 10 on this antenna. Okay.
That's okay. Not a huge loss there.
Okay. So now let's add some. Oh, there's another piece to this equation. Remember
your feed line?
Well, no, this wire, this one here, is laying on top of the trees.
So it's got a.
It's got all kinds of issues. It's in the summertime. Those trees are full of leaves.
It's got a higher impedance that way.
The tree is full of sap, and so it's shorting RF, some of it, to ground. So current flowing in this wire is different than the current flowing in this wire. This one is out in the clear. This one is not. So I have an imbalance. Okay? In the wintertime, it's still imbalanced, but it's more balanced because there's no foliage in the tree. It's a better situation. Okay, so now here we go. Let's add some loading coils. Okay, I ticked. So let's run it again. So this is 10 meters now with loading coils. Okay. Now,
drastically
there's a change. And I'm not concerned with the red. I'm not concerned with what the match is. I'm concerned with where does the signal go? So there's some interference. So these are fighting against this one because I've got the coil here and a coil here now. Less like a beverage, more in the direction broadside, which is what I would expect. So now if I do the color picture, okay, it's not perfect, wow, but it's better.
It's much better.
Yeah.
Much better. And we're still on 10, right?
This is 10 meters, right? Okay. And so this picture does coincide with what I have encountered since I put these coils on. It does play more in the. I hear the West Coast on 10 much. The other day, I mentioned to you, I was it was actually 11 meters, so it was wide open.
Right.
And I was on an SDR in Washington State, and I dropped a 1 watt carrier, and I saw the blip. That's
That's
pretty good.
cool.
Now,
That's
I know that's the ionosphere playing tricks. It's not really my antenna that's doing the heavy lifting, but I would be willing to bet that if I were to pull those coils off and do the same thing, the signal would be a lot less. Because on 10 meters, it's now a little bit more focused in the direction that I want. Oh, I don't know. 15 meters. Let's see.
That's so strange that my very first experience in HF and HF antennas, and I chose the most difficult pain in the ass antenna to fixate on.
Oh, the end-fed half wave mean?
Yes, sir.
Yeah.
And that's where I got my
Yeah.
my coil winding I don't know what you want to call it.
Yeah. Well, some of us like a
Fascination.
challenge, and that's all good. That's wonderful.
Yeah.
I'm simply saying that for somebody starting out, that math is not their thing, antennas are not they just want to make contacts. They just want to get that reward for having their ticket that they just got, and then maybe down the road, next month, next year, then they want to do antennas. But they need a carrot. They need a prize, So start them off with something simple. Do the dipole thing. And that's why we see that in all of the antenna books. That's chapter 1 for the antenna book, is the simple dipole.
You can't mess it up.
It's almost foolproof, right?
It really is.
So this is my
Go ahead.
antenna at 15 meters now. So
Oh,
again,
wow, that's even better.
yeah,
15's a
it's
banger.
better, right? So
Man,
so
even favoring Europe.
yep. So try to picture that. Okay, you got it in your eye. What it looks
Yeah,
like.
yeah.
Okay, let's lose the coils, and I will run it again.
It'd be nice if there was a checkbox on the tuner, right?
Well, there is. I can open a second copy, but it's just I've already got it. So
No, I mean it'd be nice if you could just bypass the coils on the antenna itself.
Okay, look at it now.
What have we done? We've lost our loads.
This is without the coils. Same 15 meters, same frequency without the coils now. Look at where all the energy is. It's going up and it's going out in the direction of the wire, not broadside to it. So the point is that this doublet is really made for 75 meters, and it will do all of the harmonics because it's a doublet, because it's fed with balanced line, 600 ohm. But the signal doesn't go where you want it to on the upper harmonics, and that's physics, because these blue current humps are going in opposite directions from each other. So let's say this one is going to the right, this one is going to the left, this one again now goes to the right. So it's like these two cancel. They radiate, but they mess up this one, and these two mess up this one. And the whole thing becomes a hodgepodge, and you get this. But once you put those coils in, now there's very little current here and little current here. Most of the lion's share is on this one and on this one, because after it, this is where the coil is.
Right.
Okay.
That answers my question. I wanted to know why you picked that point. You picked that
point
for
a reason, absolutely,
for a very specific reason. So am I to guess that that's a third out?
No, it's
No?
on this frequency, it's a third. I did it at 10.
Right.
Yeah, I did it at 10, so I have 4. So all I really did was I went a quarter wave out on each side of the center. So this is the eighth harmonic. That's why there are 4 humps on the right and 4 on the left. There's a total of 8 humps. This is the eighth harmonic for this antenna. So my coil is right here and right
Okay.
here.
So just a little more than a quarter out. However you want to look at it.
On each side,
Yeah.
right. Yes, so it's an eighth of the way total end to end. Right. Yeah. Yep.
I've been staring at this G5 RV in a bag here
Mm-hmm.
with balance line, and I'm thinking I'm going to put a 1-to-1 on the ground
Mm-hmm.
and balanced up and just use just as much damn wire as possible, and then model it, and then maybe put some slight loading coils in there if it turns out to be unfavorable. Oh, and not only did I choose the infed to be my whole bit,
Mm-hmm.
um, I fed it facing the wrong direction.
Mm-hmm.
I've
Mm-hmm.
learned this entire time. I cannot believe it when I modeled it, because it's the higher the frequency, they start running
Right.
off,
Right.
especially in infed, it starts shooting off in one
Yep.
direction. And let's see, which way was I shooting off? Oh yeah, just barely up the coast of the United
Mm-hmm.
States.
Mm-hmm.
That's where all my energy was. Just that's why I was constantly getting New York. I'm like, can I please get somebody else besides Kentucky and New
So
York?
so again, so you nailed it. So this is what you just said is really, really important. And this is why I'm going to echo it with this is what my mentor told me. When you build the antenna, you find out where do you want the signal to go? Forget about match. Where do you want the signal to go? Who do you want to talk to? You build the antenna to put the signal in that direction. Then you match it. Okay. So a lot of us look at the matching first. We're chasing it. We're trimming the antenna. We're getting the best visual first, and that's fine. But it's it's the cart before the horse, because you could end up with what I just showed you on mine, this, and it's facing the wrong way. I got a great match there, but it's facing the wrong way. So nobody's going to hear me. They will, but I still make contacts with it, but I don't
It's
get.
a little rough.
Yeah, I
Yeah.
could get a lot more signal to them by adding those coils or moving the antenna. And I can't move the antenna because it's on trees, you know. But it is what it is. Um, I got a ton. Listen, I'm going to share
Yeah.
the screen back to you because this is your thing. This is your show.
Oh,
Um,
are you kidding me?
but but I have so much to share.
That's great.
This is
We
your
can.
your this is your typical ZEP. All right, so it's a half wave wire, and instead of a transformer, they use 600 ohm line, and the line is a quarter wavelength long. Because why? At the end of the wire, like I taught you, Ziggy, at the end it's always high impedance because it can't. It's the end of the wire; it can't go anywhere. So
Right.
we work our way back. So we know
Can't,
this is
can't have any
high,
current there.
right? So I know this point. Let me zoom in a little bit. So I know that this insulator, this part right here, is really, really high impedance. And I know that a quarter wave back from that, you tell me,
High impedance, low
it's
impedance.
going to be low impedance here in the center because it's 90 degrees away from this. Remember, this is a half wave antenna, so it's 180 degrees end to end. So it's 90 degrees in the middle, high current, low impedance. And then I get to here, and what do I have?
The inverse.
Yeah, this is
Yeah.
high impedance again, just like it is here. So I need to feed my transmitter or my transmitter to feed the antenna. How can I do that? Well, if I use a transmission line, forget about what kind of line, it's a transmission line and it's a quarter wavelength long, just like our antenna in the middle, it's going to flip it. It's high impedance here, and at the end, it'll be low impedance, and it'll be a match for my transmitter.
It's how I've discovered I can use 75 ohm coax to do a dipole impedance transformation for me. Yeah.
And anybody new looks at this and they go, "Wait a minute, how this can't work?"
Where's the other half of that?
Right. There's nothing connected here. There's nothing
there is.
connected there.
You're looking at it.
Yeah. Well, it's two insulators. So where
Right.
does the power go? But it does. So, and then you can get into more complex things like if
sliding impedance match.
if I don't have exactly 90 degrees of transmission line, I have a little bit longer than 90 degrees or a little bit shorter, and I create a short. I connect these wires together. At some point, I know that that's 0 ohms. I know that is high impedance, maybe 5,000 ohms. I'm picking a number out of the air. So let's say that's 5,000. We know that's 0 because it's got a short across it. At some point, I can connect my feeder where this happens to be 600 ohm line. At some point, there's going to be 600 ohms at that juncture. Or if I use coax, it'll be down here. It'll be 50 ohms or 75, a little bit above that. But that's still a match. It's using this transmission line as the match. And you know what? Now look at it and say, doesn't that look like a J-pole? I got a half wave over a quarter wave, and I got a short at the bottom. That's where the J-pole comes from. It's this guy, C. Okay. So, and I'll send you this link if you like. There's, and then you can do open instead of a short. So now this one, F, is the opposite of this. Low impedance here, high impedance here. A quarter wave down, it flips it. It's lower. I'm forcing it now because I got a short. So it's 0 here, and at some point up from 0 is 600 ohms, and it's a match to my transmission line. Okay, this one does the opposite. This is a quarter wave on each side. It's a half wave total, but I'm feeding in the middle. So in the center, this is low. This is a dipole. This is low impedance here, 75 ohms. And on my transmission line, if it's a quarter wavelength long, down here, I have 5,000 ohms because it's a quarter wave away. And at some point, 75 here, if I go down to some point, it will be 600 ohms. And again, a match for my balanced line. This is old school. This is what, listen, I started with coax, and I started with 4-to-1 transformers and and off center fed, and they worked.
And they are common mode machines.
Yeah, I had that problem, and I also wanted to be. I like tuners, so I bought a bunch of tuners, and I'm feeding the tuner into the coax, and it's fighting me. And finally, I said, what did the old timers do? And I read up on it, and they did 600 ohm. I said, well, I've got it out. My shack faces the backyard. Let's drill 2 holes in the wall.
Yeah.
Try it. So anyway, I'm going to kick it back to you.
Yeah. What? I guess I've got to relinquish. I don't want to remove Hollywood. I think you have to stop sharing your screen. Maybe?
I did.
Oh no! Wait a minute. I don't have anything.
No, you've got it.
I am not the focus. Now
Yep.
I am the focus.
Yep.
I was on 75 meters, and I'm talking to a guy, and we're talking about our antennas. And he asked me, I'm like, I'm new. What do you got, kid? And I was like, I got an infed. And he goes, oh. He goes, those are all the rage these days.
They are, yeah.
And he goes, is that thing noisy? I'm like, I mean, not really. He's like, have you ever been on a loop? And I said, no.
Mm-hmm.
And he goes, you don't know what you're missing.
He's right.
Yeah. And I said, well, what antenna do you have? And he goes, well, right now I'm talking to you on a loop. And then I hear click. Right now I'm talking to you on my Zep. And I'm like, oh my God.
Uh-huh. Uh-huh. Yeah.
And I heard him say that he had a Zep antenna. And I was like, well, I'll just be quiet. I need to listen
That's the
more.
beauty of this, is that
Talk
there's
less.
always something. There's always something to learn at every turn, or there's an antenna that we haven't played with yet.
Liberty wants to know how tall your
It's
doublet
sadly,
is.
Liberty, it's not very tall. It's only about 30 feet up, 10 meters. That's
Yeah.
it. Because I've got my water table is only 3 feet down. I got a saltwater swamp in the backyard, and if I dig a hole and I put my arm in the hole, because I got a fence out front, and I had to put a new fence post in, and my fingers are in the wet, which is great for RF. I mean, if I got a DX commander in here, it would be killer. But the doublet works great. And the beauty of the doublet is that when the storm approaches, I go outside and I disconnect off the lanyard 2 ropes, and the whole thing comes right down quick, and it goes up just as quick. It's
Right on, Hollywood.
Yeah.
I just picked something out of the hat here. I'll have to figure out what the hell this is. Offset non-resonant dipole.
Mm-hmm.
I can't for the life of me, Alan. Maybe I can turn down the zoom currents a little bit. And I'm staring at it from the top also. Come on, get your bearings. Whoa. Holy current. This thing's crazy. And then I want to thank everybody for hanging out with me in Hollywood this evening. Hollywood, or I'm sorry, Liberty Caves, right? Hollywood. You were the birthday present. I appreciate
Awesome.
it. This is great. I had a blast.
Oh,
Let's
me
do
too.
it again.
Anytime.
All right.
All right, brother.
Thanks, guys. I'm gonna hit the button.
Okay. See you later.
Adios.
Bye.